Welcome to the Deep Dive. We're your shortcut to getting informed, cutting through the noise to the core ideas.
Glad to be here.
Today, we're diving into predictive analytics and statistical learning. It's everywhere, isn't it?
Oh, absolutely. Think about it. Movie recommendations, online ads, even things like medical diagnostics. Predictions are shaping so much.
And for this deep dive, our sources are pretty solid. A university syllabus introductory notes. So we're getting a really foundational view of how we use data to make these predictions.
Exactly. And our mission really is to pull out the key nuggets. What is statistical learning? What are the main flavors? What makes it hard?
And those fundamental trade-offs, right? The ones you always have to make when you're building these models.
Yep. The goal is to equip you, the listener, to really understand this stuff, not just see the headlines.
Okay, so let's start with the big picture. I gather there are sort of two main branches here.
That's a good way to think about it. You've got supervised learning on one side. That's where you have a specific target, an outcome you want to predict.
Like predicting house prices, or whether an email is spam.
Precisely. And then the other branch is unsupervised learning. That's more exploratory.
Finding patterns, maybe?
Yeah.
Grouping similar things together without a predefined answer you're looking for?
Exactly. No specific outcome variable guiding you. It's about uncovering structure in the data itself.
Okay, let's dig into the foundations then. What exactly is statistical learning?
At its heart, it's really a set of tools, a framework for understanding data, and specifically understanding the relationship between different measurements.
Right, so you measure different things and try to see how they connect.
Yep. And you usually have two main players. First, there's the outcome, what you're trying to predict or understand.
That's the Y variable, right? Sometimes called the dependent variable or target.
Exactly. Why? And then you have the things you use to make the prediction. Those are your predictors.
The inputs, features, independent variables, lots of names for those too. The X's?
The X's, yeah. Our source material uses a great simple example, trying to predict product sales, which is Y. And you'd use inputs like spending on TV ads, radio ads, newspaper ads. Those are your X's.
So you're looking for some kind of relationship, like sales is some function of TV, radio, and newspaper spending.
Precisely. We write it sort of abstractly as Y equals FX plus A. That F is the unknown function we're trying to figure out.
And what's the epsilon?
Ah, epsilon. That's crucial. Represents everything else, measurement error, factors we haven't measured, just inherent randomness. It's the bit our function f can't explain.
Okay, so finding a good FX seems pretty important. What are the big payoffs?
Well, there are two main ones. The first is prediction, obviously. If you have a good FX, you can plug in new values of X, say new advertising spends, and get a pretty good estimate of what Y the sales will be.
Makes sense. That's the predictive power.
But the second payoff is arguably even more interesting. It's about understanding.
How so?
A good model can tell you which of the X's actually matter for Y and how they matter. The source mentions an income example, right?
Yeah, I think so. Like seniority and education affect income.
Exactly. The model might show those are important predictors, but it might also show that, say, marital status doesn't really have a significant impact on income in that particular data set.
Ah, I see. So it's not just predicting a number, it's understanding the drivers behind that number. That's really powerful insight.
It is. It moves beyond just forecasting into explaining the why.
Okay, so let's focus back on supervised learning for a minute. The goal seems pretty clear-cut there.
Yeah, it's more defined. You start with your training data, pairs of X's and Y's that you already know, like AR1, Y1, on A2, Y2, and so on.
Your historical data.
Right. And from that, you want to, well, first, predict Y for new X's the model hasn't seen.
The test cases.
Yep. Second, you want to understand those input effects, like we just talked about, which X's matter.
And third,
you need to know how good your predictions actually are. Assess the quality, the accuracy.
okay. And within supervised learning, there are different problem types.
Two main ones, generally. Regression problems. That's when your Y, your outcome, is a quantitative number.
Like price, age, blood pressure.
Yeah.
Something you can measure on a scale.
Exactly. And the other type is classification.
That's when Y is categorical, right? Like categories or labels.
Perfect. Y belongs to a finite set of classes. Survived or died, spam or not spam, which digit from 0 to 9, which type of cancer tissue, things like that.
Okay, that distinction is clear. Supervised has that target. But unsupervised, you said that's fuzzier.
Yeah, fuzzier is a good word for it, because with unsupervised learning, you don't have a Y variable. You just have a bunch of X's, a set of measurements on different samples.
So what are you trying to do then if there's no target to predict?
Well, the goals are less concrete. You might be looking for natural groupings or clusters in your data. Are some samples inherently similar to each other based on their X values?
Like customer segmentation, maybe?
That's a classic example. Or maybe you're trying to find features that tend to vary together. Or sometimes you're looking for ways to reduce the number of features, finding combinations that capture most of the information.
So it's more about discovering hidden structure.
Exactly, discovering structure. The downside is it's harder to know if you've done a good job because there's no right answer, no why to compare against,
Right.
no ground truth. But it's still incredibly useful. Often, unsupervised learning is used as a first step, like a pre-processing step, before you even start building a supervised model.
Interesting. Okay, so whether it's supervised or unsupervised, we're often thinking about this function fx. Is there like a theoretical best possible version of this function we're aiming for?
There is, in theory. For prediction, especially in regression, the ideal target is what's called the regression function. It's written as f(x)(ey)(x) equals x.
Okay, what did that mean in plain English?
Is-
E is expected value.
Yeah, expected value. So it's the average value of y, given that x has a specific value, a little x. If you knew this function, it would give you the best possible prediction in terms of minimizing the average squared error.
The mean squared error. Okay, so that's the gold standard.
It's the theoretical target, yeah.
But even if we knew that perfect ideal function, we'd still make mistakes. You mentioned that epsilon term earlier.
Absolutely. That's a really key point. Even with the perfect fx, there's still error. That's the irreducible error. It's the epsilon. It's y(y)(fx).
Why is it irreducible?
Because for any given set of inputs x, there isn't just one single possible value for y. There's usually a whole distribution of possible y values. Think about predicting someone's income based on education and experience. Even for people with the exact same education and experience, their incomes will vary, right?
Sure. Lots of other factors, plus maybe just random chance.
Exactly. That variation, that inherent noise or randomness in the world, that's the irreducible error. No model, no matter how good, can predict that part perfectly.
So our goal isn't to eliminate all error, because we can't.
Right. Our goal is to minimize the reducible error. That's the error that comes from our estimated function, let's call it x, ff, being different from the true ideal fx. We want our estimate to be as close as possible to the true underlying function.
Okay, so how do we actually estimate this fx from real data, since we usually don't know the true function?
Well, one intuitive approach, especially if you have lots of data, is local averaging.
Local averaging.
Yeah, the idea is to estimate the function fx at a particular point x, you look at the y values for all the training data points that are close to x in its neighborhood, and you just average them.
So x is roughly the average of y for x values near x.
Pretty much. X is yx, nx, where nx is the neighborhood around x. Methods like k-nearest neighbors sort of work on this principle.
K-nearest neighbors, looking at the k closest data points.
Exactly. And these local methods can actually work quite well if
what?
If you have a small number of predictors, let's say p, the number of x variables is maybe 4 or less, and if you have a ton of data points, n.
So there's a catch. What happens when p, the number of predictors, gets large? I feel like this is leading to the famous curse of dimensionality.
You nailed it. This is where the intuition breaks down spectacularly. When pro is large, these simple local averaging methods, like nearest neighbors, become, well, the source says lousy, and that's not far off.
What goes wrong?
The core issue is that in high-dimensional space, lots of predictors, points are just not close to each other anymore. Your newest neighbors can actually be really far away.
That seems counterintuitive.
Yeah.
How can the nearest neighbor be far away?
Okay, think about it like this. Imagine you need to define a neighborhood around a point X that captures, say, 10% of the total data.
Okay.
In one dimension, just on a line, that neighborhood is a tiny little segment. It's truly local.
Right, a small interval.
Now go to 2 dimensions, a square. To capture that same 10% of the data points, your neighborhood, maybe a circle, has to have a significantly larger radius. It has to stretch out more.
Okay, yeah, the area needs to cover 10%.
Now jump to 3 dimensions. A cube, that sphere capturing 10% of the points gets even bigger relative to the total space. Keep going. 10 dimensions, 100 dimensions.
Whoa. So to capture that same 10% fraction, the neighborhood has to become enormous.
Enormous. It basically has to cover a huge fraction of the range of each predictor variable. So the points inside that neighborhood are no longer actually local to your target point X. They're far away in many dimensions.
which means averaging their y values doesn't really tell you much about fx at the specific point x anymore.
Exactly. The averaging becomes meaningless because you've lost locality. That's the curse. High dimensions make space vast and empty, and the concept of a close neighbor loses its practical meaning.
Wow. Okay, that really changes things. So if simple local averaging falls apart, what's the alternative for high-dimensional data?
This is where we need more structured approaches. We often turn to parametric models.
Parametric, meaning they have a predefined form with parameters.
Exactly. The classic example is the linear model. FLX equals 0 plus, Bro x1 plus beta 1 plus beat xp.
Good old linear regression. Beta 0 plus beta 1 x1, etc.
Yep. Here, we assume the function fx has this specific linear form. We don't need to worry about local neighborhoods anymore. We just need to estimate a fixed number of parameters, the betas, 0, 0, 0, boring kata, from the data.
And the benefit is this works even with many predictors, many x's.
It can, yes. It avoids the curse of dimensionality by imposing the strong structural assumption linearity. It's simple, it's highly interpretable. You can look at the beta coefficients and see the estimated effect of each x.
Even if the true relationship isn't perfectly linear.
Right. Even if the true fx is way more complicated, a linear model can often be a really useful approximation. It might capture the main trends. And sometimes you can extend it, like using quadratic terms or interactions, to make it a bit more flexible while still being parametric.
Okay, so parametric models like linear regression give us structure and interpretability, helping with high dimensions. But what if that structure is just wrong? What if the real relationship is super complex and nonlinear?
Then you might need to move towards more flexible models. Models that don't make such strong assumptions about the shape of fx.
Like what kinds of models?
The source mentions things like thin plate splines. You can think of these as fitting a very smooth, flexible surface to the data, bending and curving to capture complex patterns. They have more degrees of freedom, allowing them to adapt much more closely to the data.
That sounds powerful. More flexible means it can capture more nuance.
It can, but there's a danger lurking there.
Ah, the danger of too much flexibility. Is this where overfitting comes in?
Precisely. Overfitting is the big pitfall of highly flexible models. It's what happens when your model learns the training data too well.
Too well? How can it learn too well?
It starts fitting the noise, the random quirks, the specific anomalies in your training dataset, not just the underlying signal or true pattern. It makes almost zero errors on the data it was trained on.
Which sounds good.
But that incredibly tight fit doesn't generalize. When you show it new data it hasn't seen before, it performs terribly.
Because it learned the noise, not the real pattern.
Exactly. The source has this great visualization of an even more flexible spline model for that income data. It literally wiggles and contorts itself to pass through every single training data point.
Wow. Perfect fit on training data.
Perfect fit, zero training error. But it's clearly insane, right? It's just memorize the training set, noise and all. That's overfitting in action. It won't predict new people's income accurately at all.
Okay, so it's a balancing act then. You need flexibility to capture real patterns, but not so much that you just memorize noise.
That's the constant tension.
So what are the key trade-offs we're always juggling here?
Well, one big one is prediction accuracy versus interpretability.
Right. Simple linear models are easy to understand, but maybe less accurate.
Often, yeah. And those super flexible models like complex splines or deep learning networks might be incredibly accurate predictors. But trying to understand why they make a certain prediction can be really difficult. They can be black boxes.
Okay. Accuracy versus understanding. What else?
There's the trade-off between a good fit versus over-under fitting. We want a model that fits the true patterns well, but we desperately want to avoid overfitting the noise and also avoid underfitting being too simple and missing the pattern altogether.
Finding that Goldilocks level of complexity, not too simple, not too complex, but just right.
Exactly. And related to that is a preference for parsimony versus black box. Generally, if two models give similar prediction accuracy, we prefer the simpler one, the one with fewer variables or assumptions. It's often more robust and easier to trust.
So it sounds like there's a whole spectrum.
There really is. You can sort of place different methods along a spectrum of flexibility versus interpretability.
Can you give some examples? Where would different methods fall?
Sure. On the high interpretability, often lower flexibility end, you might have things like choosing the best subset of predictors for a linear model, or techniques like the lasso, which tend to simplify models.
Okay, simple and clear.
Then in the middle, you've got your standard least squares linear regression, maybe generalized additive models, GAMs, which allow some nonlinearity but are still fairly interpretable, and decision trees.
A bit more flexible, maybe a bit harder to interpret.
Right. And then way over on the high flexibility end, often giving state-of-the-art accuracy but potentially being much less interpretable, you find methods like support vector machines, SVMs, boosting, and of course, deep learning.
So you're constantly choosing where on that spectrum you need to be for a given problem.
Absolutely. It depends on your goals. Is prediction accuracy paramount?
What are...
Or is understanding the why more important?
Okay, so if overfitting is such a danger and fitting the training data perfectly is misleading, how do we actually know if our model is any good? How do we assess its accuracy properly?
This is maybe the single most important practical point. You cannot trust the error metric calculated on the data you use to train the model.
That's the mean squared error on the training data, the MSETR.
Right. The MSETR will almost always go down as you make the model more complex, more flexible. It actively encourages overfitting. It gives you a misleadingly optimistic view of how well your model performs.
So it looks great on paper, but fails in the real world.
Precisely. The only reliable way to assess how well your model will actually perform on new unseen data is to test it on, well, new unseen data.
Fresh test data.
Yeah.
Data the model was not trained on.
Exactly. You calculate the mean squared error on this separate test set, the MSE. That MSE gives you a much more realistic, unbiased estimate of how your model will generalize. That's the number you should care about.
Okay, test data is critical. Now, you mentioned finding that Goldilocks point, not too simple, not too complex. This sounds like it connects to the bias-variance trade-off. I hear that term constantly. Can we break that down?
Yes. This is the fundamental concept that explains why there's an optimal level of flexibility. It really gets to the heart of model complexity.
Okay, lay it on me.
So that expected test error, the MSE that we care about, can be mathematically decomposed into 3 pieces.
3 pieces.
Yep. The first is variance, the second is bias squared, and the third is that irreducible error, epsilon, that we talked about earlier, the noise we can't do anything about.
Okay, variance and bias. What do those mean intuitively?
Oh,
Let's use that dartboard analogy, maybe.
Okay, good idea. Imagine you're building the same type of model many times, but each time using a slightly different training data set drawn from the same underlying source.
Right.
Variance refers to how much your model's predictions, X, would change if you trained it on these different data sets. A high variance model is very sensitive to the specific training data. Its predictions jump around a lot depending on which data it saw. Think scattered shots all over the dartboard.
So flexible models tend to have high variance because they fit the specific noise in each data set.
Generally, yes. More flexibility often leads to higher variance.
Okay, what about bias?
Bias refers to the error introduced by approximating a real-life, potentially very complicated problem with a simpler model. It's how far off, on average, our model's predictions are from the true underlying function fx. A high bias model makes strong assumptions that might not be true. Think aiming consistently off the bullseye, even if your shots are tightly grouped.
So simpler models like linear regression might have high bias if the tree relationship isn't linear.
Exactly. They might miss the true complexity, leading to systematic error or bias. Less flexible models tend to have higher bias.
So flexibility decreases bias but increases variance.
That's the core trade-off. As you increase model flexibility,
Okay.
bias tends to go down because the model can capture more complex patterns, getting closer to the true fx.
Makes sense.
But variance tends to go up because the model becomes more sensitive to the noise and fluctuations in the specific training data it sees.
Okay. So how does this relate to the test error, the MST?
The total expected test error is basically variance plus bias 2 plus irreducible error. So when flexibility is low, bias is high, variance is low, the error is dominated by bias.
Right. The model is too simple.
As you increase flexibility, bias drops, which is good. Initially, this drop in bias outweighs any increase in variance, so the total test error goes down.
Okay, we're improving.
But if you keep increasing flexibility, eventually bias becomes very small, but variance starts to climb rapidly as the model overfits. Now the error is dominated by variance.
And the total test error starts going back up.
Exactly. That's what creates that characteristic U-shape for the test error curve when plotted against model flexibility. It goes down, hits a minimum point, and then goes back up.
And that minimum point,
Yeah.
That's the sweet spot, the Goldilocks model.
That's the magic point. That's the optimal level of flexibility that minimizes the overall test error. It strikes the best possible balance between bias and variance for that particular problem and dataset. Finding that point is the art and science of statistical learning.
That U-shaped visualization really clarifies it. Low flexibility equals high bias. High flexibility equals high variance. Somewhere in the middle minimizes the total error on unseen data.
You got it. That's the fundamental principle.
Okay, let's quickly apply this back to classification problems. We said, why is categorical? There's spamum, digit, 09, etc. What are the goals for a classifier?
Pretty similar to regression, actually. First, you want to build a rule to assign a class label to a new observation based on its X predictors.
Predict the category.
Second, you often want to assess the uncertainty of that classification. How confident are we it's really spam?
Okay, probability estimates.
And third, again, you want to understand which predictors, which X's, are important for distinguishing between the classes.
Is there a theoretical best classifier like the regression function?
Yes, there is. It's called the Bayes optimal classifier. It works by calculating the conditional probability of belonging to each class given the predictors X. So PKX, PRYX equals X.
The probability of being class K given X.
Yep. Right. The Bayes classifier simply assigns the observation to the class K for which this probability, PKX, is largest. In theory, this classifier achieves the lowest possible error rate, the Bayes error rate.
Similar to the irreducible error in regression, there's a minimum error rate you can't beat.
Exactly, because even for the same X, there might be uncertainty about the true class.
Now, how does something like k-nearest neighbors fit into classification? We talked about it for local averaging in regression.
KNN is actually a very intuitive and widely used classifier. It directly applies that neighborhood idea.
How does it work?
To classify a new point, you look at its k-nearest neighbors in the training data based on their X values. Then you basically take a majority vote among those k-neighbors. Whichever class is most common among the neighbors, that's the class you assign to the new point.
Simple enough, so it forms decision boundaries between classes based on these neighborhoods.
Right, and the value of k directly controls the flexibility of that decision boundary, showing the bias-variance trade-off beautifully.
Okay, how does k affect it? Let's say k is really small, like k1.
K1 means you just look at the single closest neighbor. This leads to a very flexible, often very jagged and complex decision boundary. It's highly sensitive to individual data points, including noise, so low bias.
But high variance, prone to overfitting.
Exactly. It fits the training data very closely, maybe too close.
What if k is larger, say
Absolutely.
k10?
With K10, you're averaging the votes of 10 neighbors. This smooths things out. The decision boundary becomes less jagged, more robust to noise. Variance decreases.
Okay, smooth the boundary.
And if you make K really large, like K100,
Then the boundary becomes...
very smooth, very rigid, you're averaging over a large neighborhood. This leads to low variance, but potentially high bias. The boundary might become too simple to capture the true separation between classes. It could underfit.
So just like in regression, we see the trade-off with k. Small k is flexible, low bias, high variance. Large k is rigid, high bias, low variance.
Precisely. And if you plot the classification error rate against 1K, since small k means high flexibility, you'll see that same U-shape for the test error rate. The training error will typically just decrease as k gets smaller, flexibility increases, but the test error finds an optimal k somewhere in the middle.
The bias-variance trade-off is truly universal then across regression and classification.
It really is the central theme in understanding model performance.
This has been incredibly clarifying. Let's try to wrap up the main takeaways from this deep dive.
Okay. We started by establishing statistical learning as this powerful framework for prediction and understanding relationships in data.
We drew that key distinction between supervised learning, predicting a target Y, and unsupervised learning, finding patterns in X alone.
We hit that major hurdle, the curse of dimensionality, realizing our low-dimensional intuition about closeness totally fails in high dimensions, pushing us away from simple local methods.
Which led us to the contrast between parametric models like linear regression, interpretable, structured but maybe too simple and flexible models like splines, powerful pattern finders, but potentially black boxes, prone to overfitting.
And that hammered home the absolute necessity of using fresh test data to get a true measure of model accuracy, because training data error, MSETR, is just dangerously misleading.
Right. Don't trust the training score.
And finally, it all culminated in the bias-variance trade-off. This is the core principle. The test error is composed of variance, bias squared, and irreducible error. Increasing flexibility usually lowers bias, but raises variance.
And the goal is finding that sweet spot, that minimum point on the U-shaped test error curve, which gives the best generalization performance by balancing bias and variance.
That's the essence of it.
Fantastic. So thinking about how pervasive this all is, predictive models are everywhere, shaping recommendations, financial decisions, medical insights.
Yeah.
It leads to a final thought. Given everything we've discussed, especially the bias-variance trade-off, how might understanding this change how you, the listener, interact with or evaluate the smart systems around you every day?
That's interesting.
Are the recommendations you get potentially overfit to narrow data, maybe not generalizing well? Is that medical diagnostic tool perhaps too rigid, maybe missing subtle edge cases because it's biased towards simplicity?
Yeah, is it high bias or high variance in disguise?
Exactly. Understanding these fundamental trade-offs isn't just academic. It empowers you to be a more critical, informed user, maybe even a participant in this data-driven world, questioning the predictions that increasingly shape our lives. Something to think about.